specialized foundation models. So how people have developed foundation models for applications beyond text and images. And I'll go over kind of the large-scale pre-training paradigm that people have been doing. Okay, and that's good. Great, thank you. Yeah, so the large-scale pre-training paradigm of how we actually train these models beyond text, and our investigation into the latest specialized foundation models and a comparison of them to kind of the alternative, which is classical supervised models. This first part will in some ways depend on the second part. So I think the top story is the first part, but were some methodological innovations underlying our investigation of these specialized foundation models that were driven by developments in architecture research that we also spearheaded over the last couple of years or so. And I'll go into what kind of the state of art in architecture search is and how we were able to apply it to this investigation of specialized foundation models, because we were able to develop architecture search methods that didn't just work for images, which was the dominant paradigm of architecture search research for a very long time, but also worked beyond vision and text. And so the first part of this work was led by, I'm going to get rid of this. The first part of this work was led by Zhang Zhu, who also goes by Stone at Ritwik. So they were master's students at TMU at the time. And I guess Stone is now at USC, a PhD student, and Ritwik is at Cortical AI. And then the rest are further collaborators at TMU, Wendo, Alex, Junhong, and Amit Talwalkar.
Height floating. Oh, you had it. Yeah, you had it.
Height floating. Great. Okay. So the first part of my talk will be about specialized foundation models, and to understand this development, I want to go back in time for about a decade, maybe a little more, and understand some paradigm shifts in AI and understand where we are, right, and where different fields are, where text is, where vision is, and where things beyond vision and text are. Now my clicker doesn't. Okay, so in 2012, as many of you know, there was the ImageNet moment, right, where previously we were training models that were often not neural networks, and we were not training them on as much data. In ImageNet, we were able to put the training of deep learning on GPUs and train neural networks that did extremely well in image classification, and this kind of spurred the deep learning boom over the following decade or so. I think that in 2018, there was a further paradigm shift in machine learning, and I'm going to call it the BERT moment. And this is not a term we coined, but we use it in the paper. It's less used, I think, than ImageNet moment. But the BERT moment was when, instead of training deep nets on one set of data and testing on the same set of data from the same distribution, we started doing pre-training. Specifically on text. So we started pre-training on these massive text corpora and tuning them on supervised tasks. And this quickly kind of became the dominant paradigm for how we did machine learning, instead of, or at least to get state-of-the-art on applications same text. In 2022, of course, as all of you know, in-context learning was kind of developed with the GPT series, culminating with, of course, ChatGPT, where we are now able to learn just from doing kind of language prediction. But this part I will not be talking about in this talk. I know you're all very excited about it, but I will be focusing on the BERT moment. And the reason, of course, I'll be focusing on the BERT moment is because I don't think we're anywhere near this ChatGPT moment with applications beyond vision and text. I would, in fact, the point of this talk is to maybe also question whether we have even reached this BERT moment with applications beyond vision. So why do I view this as a paradigm shift? So before we fit neural networks directly on supervised data, so labeled pairs X and Y, and this did reasonably well. After BERT was introduced, certainly in NLP, at least in natural language processing, everybody switched to fine-tuning foundation models on pre-trained massive data sets. So this is the only way you could obtain state-of-the-art on any task in natural methods. And so what to understand what you mean here, what is supervised learning? We have some labeled pairs X, Y. Say we're doing spam classification. We choose some parameterized model or class of functions that maps from these input data to the output data. And we set the parameters of this function by optimizing performance on the data that we have. So say to maximize the accuracy of our classifier. And then we tune as needed. So this is the pipeline of supervised learning. And we'll be returning back to what this pipeline is. Hopefully, and maybe in a cartoon form, what we have is when we want to do a traditional supervised learning workflow is we do some model development. So we look at our data very thoughtfully. And we develop some, say, network architecture. We do some hyperparameter optimization around this network architecture. Then we train our model on a target task. And maybe we do some looping, right? We tune as needed. And so what happened in 2018? Well, Google trained this large model, BERT, to fill in masked words in things like Wikipedia and large corpora of books. And the kind of key development of BERT is that when you adapt this model, so adapt the representation by this model on supervised tasks, so kind of start with those representations and then transfer learning to supervised setting. BERT did dramatically better across the board on natural language processing tasks. And so here we use BERT as either an initialization, or we can use it like as a representation for these text tasks. And at the time, these models were not being called foundation models, but later they were called foundation models. At the time, at least, this was a controversial name, but for simplicity, we'll stick to that term for what we're talking about today. So BERT and kind of other models that were got even larger, were termed foundation models because they served as a foundation. You pre-trained on a lot of data, and then it was a foundation for doing well on a bunch of other tasks. So now we have this alternative workflow. Right? You pre-train your foundation model on a massive data set. Many of you probably will have to download it. You optimize your performance on your data, so similar to the training, but now we're going to call this fine-tuning. You fine-tune your foundation model on some target task. And then you tune this pipeline also as needed. So somewhat similar, but you start with this massive pre-trained model, and we call it fine-tuning instead of training. And maybe numerically, why this was a paradigm shift was because it did a lot better on the benchmarks people cared about at the time. And I guess recently, more benchmarks have been developed, and of course, we still use foundation models. And so I'll be, again, returning to this plot also. But on this plot, what I'm plotting is the total number of pre-training plus fine-tuning tokens in the task. So you can view this as like the amount of data we have for the task. And this is a log scale. And on the x-axis, I'm plotting kind of shifted improvement in the GLUE score. So GLUE was this very ancient benchmark in like 2018, where there were like 10 or 9 tasks in natural language processing. And you did things like classification and inference, like whether something can be an inference from something else, and so on. And before BERT was introduced, the best way to do this using a supervised approach was something called a bidirectional LSTM or bi-LSTM. And this was this fancy model. It went back and forth. It was a recurrent, not fun to train. You trained it on your task and you got some score, and we can use that as the baseline. So the GLUE score here is shifted. And then BERT was introduced, and it did almost 20% better, right? So you have a 0.2 on the y-axis. And from then forward, additional models were introduced, XLNet, T5. This is, of course, still very old. This is up to 15. But it was a paradigm shift because you got this massive improvement in performance as you increased the total number of pre-training plus fine-tuning tokens that you're using. So here we're using a lot fewer tokens, but we get also worse performance. And you can see as performance scales, you do a lot better. So this is what happened in natural language processing. More recently, there has been a massive explosion of interest in specialized foundation models. So foundation models have adapted to many other types of data, from speech to structured data to scientific tasks, biology tasks, and so on. And why? Well, many data sets that you all might have and that people have in the world that have massive unlabeled data sets just lying around train on them, right? People saw this, and people saw the obvious success in things like text, in things like vision, in audio with the Whisper model, and so on. So there was a lot of success with these foundation models in the kind of classical AI domains with signals, and to build upon this, and also driven by, of course, a good dose of hype, lots of specialized foundation models have been introduced since then. And kind of the example paradigm here, and I'll use an example from scientific computing, which I won't go further into so much, but an example here is there's a foundation model, say, called Poseidon, for doing PD solving. And what they do is they gather up a bunch of simulations of partial differential equations. So basically, you map from one state of the fluid to the entire trajectory of the fluid. They pre-train on this large collection of simulations. They train a model of size 600 million, which is pretty big. It's not the scale of the largest models at all, but it's pretty big. It's bigger than BERT. And then they fine-tune it on other PD tasks, so PDs solving different equations. And this is kind of the paradigm that people want to do, right? They want to take a bunch of simulation data, say they have lying around, and maybe speed up simulations or get like rough estimates of future simulations. And the similar type of approach has been done on a variety of tasks. So in computer vision, of course, this somewhat predates BERT, so we won't be talking about it so much. In fluid dynamics and PD solving, there is very few well-known foundation models other than the one I just showed. So we won't be focusing on that so much in this talk. In this talk, I'll be focusing on three specific domains because they've had a lot of work in these specialized foundation models. And the specific domains I'll be talking about is work on genomic sequences. So we have trillions of human genome base pairs. The idea is let's train on them. There are more than 10 foundation models that have this like a kind of 100 million parameter range or higher, including rather big ones. Like there's a 2.5B model in this gold. At this point, I think there's a 7B model. There's also a second modality we'll be looking at is satellite imaging. So here you have millions of pictures of Earth, also a strong candidate to train on. This isn't just computer vision. There's a lot of kind of differences in satellite images versus natural images. But here also there are a lot of foundation models, also in the 100 million parameter range. And a last modality I'll be looking at is time series, which is of course a very popular forecasting type. Lots and lots of time series to train on. And here there's also like on a similar order amount of foundation models, also with a large number of parameters. So the goal here will be to understand whether if we take all these foundation models, have there been BERT moments in these foundation models? Have we done better on the foundation model than like we could do on the tasks that these people said when they trained their foundation models? Can we do better on those tasks? Use their foundation models relative to a reasonable supervised baseline. And so this is kind of the outline of our investigation. We picked these three specialized domains. We picked them because they have many large foundation models. We identified the benchmark tasks that they used to say that our models are good, right? You can't release a model these days without having like a bold letter in your table, bold number. And then we asked this question, does fine-tuning those foundation models on the tasks that they set beat traditional supervised learning given the same compute budget? And but traditional supervised learning will literally be no external data, just train on the target task. So we're going to take
yes. Question. I mean, it seems like that third question would be a question posed and answered in the original quote unquote foundation model paper. So, like, wouldn't they demonstrate ability as a foundation?
Yes, they're supposed to. You mean like the specialized foundation models I like went over, like the.
Yeah, I mean, your investigation sounds like what
something they should have done. Yes,
and they didn't quite do it.
Yes, there are. I'll go into reasons why that are somewhat unique to the individual domains, why the investigations kind of failed,
Gotcha.
Or why like their results were maybe either oversold or they ignored some points.
So Misha,
yes,
clear. You're still training on the same model. You're taking the model, but
I'm not training the foundation model. I'm not training the same model. I'm training only on the same data, but I'm using other models. Similar to how like BERT, the comparison was say to bidirectional LSTM versus the BERT transformer. Here, like a lot of the foundation models are transformers or like large convolutional networks, and I'll be comparing them to smaller, mostly smaller convolutional networks. And in one case, I will also be comparing them to linear models.
So, and you pick these models, I guess, based on was there any basis for picking these models?
Yes, I'll go. There is a very the picking of the models is kind of the second part of the talk where I'm doing architecture search. So there is kind of like a somewhat more involved component that demonstrate that this can be done, but it's a bit more complicated than just one model and showing it. Like you can't do well in all of these applications or even on all individual tasks using one model. You do have to specialize to the individual domains.
Yeah, a big question. So first of all, like let's say if this comparison, I'm just trying to see if this comparison is like fair comparison because foundation models are supposed to for multiple downstream tasks and more compute on pre-training, but for downstream adaptation, you use a fewer fluffs or a smaller amount of compute. So I'm just trying to see if
the compute budget doesn't count for you.
Oh, is it the?
It's the compute budget of just fine tuning alone. I'm comparing like how expensive it is in terms of labeled data and also compute to fine tune a foundation model versus how expensive it is to do the supervised learning step. So I'm only doing a fine tuning. I'm only counting the fine tuning compute.
Oh, I see. Okay, that's clear. So, I guess you haven't mentioned the tabular and structured data domain because the same question has been answered.
Tabular, yeah.
Tabular data, structured data. Do you have any thoughts with that domain? Because there also has been like backup tabular data.
Right. Yeah. I am not sure what the state of that is right now. Even with some of these domains, things have, I think, been updated to some extent. But yes, I don't know what the state of tabular is. Okay, so our goal is going to be to compare this traditional supervised learning workflow to this foundation model workflow that I outlined. And there's going to be just one caveat, which is in traditional supervised learning, we do this model development phase where we spend a lot of time looking at our data and see what kind of model seems to work well for this data. We don't have time for this. We have a lot of tasks we want to do. And so we can't really do all of them. And so like we can't do this model development phase as kind of a small team from an academic institution. So what we're going to do is we're going to replace this and simulate the supervised learning workflow by replacing model development with a neural architecture search phase. And to preclude any further questions, this is also counted in our computation budget. So we do compare like how expensive architecture search is to doing fine tuning. All of this is still on this very same data. So we still compare on the same data, and we compare the whole budget, the like full pipeline budget here to, I guess, the budgets of the second two here. And I'll get into exactly how this architecture search is done in the second part of the talk. Okay, so remember, we measured kind of the BERT moment by how much improvement you saw as you increase the number of pre-training plus fine-tuning data that you saw. Did your performance on your benchmark go up? And we saw that for like the standard benchmark in natural language processing, this was indeed the case. You got 20% improvements or so from these foundations. So this is the results on genomics, on satellite imaging, and time series. So here I can go into what we did. So again, we have this supervised model. It's trained only on the target data, so there's a lot less training data, logarithmically less, or the scale is logarithmic. And for genomics, a tuned CNN does better than basically all of the foundation models out there. For satellite imaging, it does roughly the same. And for time series, things are a little even crazier, which is that we took an AR model. Anyone who takes an econometrics class Probably a stats, I don't know. You learn, this is the first model you learn. Linear model combines like the past data linearly, maybe does some differencing. Tuning that slightly does about as well as the time series foundation model. I'll go into more what happens here. But yeah, in even more detail, the foundation models that we discovered in genomics, they were, or the tuned CNNs that we discovered in genomics, yes.
Just to understand here, it's like neural architecture search has had 3,000 papers, right? There was like even a survey saying 3,000 papers of neural architecture search.
Yeah.
So like probably some of these papers do cover these data sets, right? So like basically they are optimized neural architecture sets for, if not these data sets in particular, for this broader set of problems, right? There are multiple papers on neural architecture search on time series, for example. While on the other hand, are there foundation models fine-tuned on these particular data sets or similar data sets? Because otherwise it's going back to what Kang was asking, right? Like, are we comparing the same thing?
I guess I'm a little confused. The foundation models are fine-tuned on time series data sets. Like,
sure, but like there are many ways to fine-tune something, right? Like I can fine-tune the last layer, I can fine-tune it like there are many hyperparameters. Even if I just do fine-tuning, while there are specific papers on neural architecture search on these datasets or similar datasets, and again, a literature that goes back at least a decade. Right? So, like basically, one thing is that like maybe neural architecture search was going to come ahead because of the experience of the community in the last 10 years, right? Since the
so I've done a lot of work on architecture search. I know that there is architecture search work for time series. There, other than work I'll talk about in this lecture, or sorry, in this talk. Sorry, I taught this morning. I am not aware of kind of certain. There are a few papers on biology and so on, satellite imaging, but it's the dominant paradigm in architecture search has very much been computer vision, and computer vision in kind of like very explicit, like how do we do better on CFAR and imaging. That like I like the benchmarks in the field, like all the NOS bench with all the numbers. They are predominantly computer vision with a little bit of time series. There's audio, of course, and there's text. So I don't know, like you can apply architecture search to these foundation models, and maybe it will do better. But of course, architecture search is a very expensive procedure when you want to do it for, say, pre-training. So I guess my point is like it depends. I guess it depends on what your question is. Like, so what is your alternative?
So my alternative would be like how close, or okay, let me rephrase. How far away was the closest paper in neural architecture search with these data sets?
How far away was the closest paper in neural architecture search with these data sets? Well, we took a neural architecture search approach that wasn't applied to these data sets. Okay, applied it, and it did well.
So how does the research do decide the data set? Because it's like a
great question. I'll have a table for that. There are some, yeah, I'll have like a plot on a copy. Okay, so we were able, at least on the first two settings, to use architecture search to discover models that are matching or outperforming foundation models that are like 10 to 100 times bigger, and kind of achieving performance that is competitive on kind of the benchmarks in those fields. For time series, we tuned an AR model that's competitive with many thousands, hundreds of thousands times bigger time series foundation model. The kind of key issue that we discovered, and I'll go into in detail, but the summary is basically that these past work and time series, they compare to linear models. Of course, you have to. They compare to linear models with 5 time steps of history, while giving their foundation models 512 time steps of history. And there is kind of a reason for this. So there is this method in time series called auto-arima. Basically, it's kind of the standard baseline. You have a linear, or sorry, you have some time series data, and you want to train an ARIMA model, which is kind of characterized by an autoregression with some number of lookback and a moving average with some number of lookback. And then the I stands for whether you take difference. And so they have these context line parameters that determine how expressive this ARIMA model is. And that's what's tuned using various statistical tests. But AutoARIMA basically by default sets P and Q to be at most 5. The reason is, like, we tried to run AutoARIMA with 512. The default implementation is too expensive. I'm sure it's possible to implement it without making it that expensive, but the kind of default software is just does not turn it. And so an early paper evaluated AutoARIMA against a bunch of supervised baselines, and the supervised baselines were doing better than AutoARIMA because AutoARIMA wasn't given a lot of context. And so these time series foundation models, they didn't do anything like explicitly wrong. They did what many of us do, which is they took number from table from previous paper. But they gave their foundation model 512 sums of context. We got rid of the Q. We found that, unsurprisingly, ARP is actually very cheap to fit with 512 models, 512 steps of history. You do some tuning, again, using statistical tests, whether you difference, whether you, how much context you give. But it does better, it does as well as these time series foundation models. So I feel like the story here is kind of a very understandable sequence of events. So at least our answer for now is that according to the tasks that these folks set, we can find architectures that do reasonably well on those tasks. The architectures are smaller. And we can get them to work better than these foundation models given similar compute budgets and the same downstream data. And so some other questions, maybe foundation models are more efficient, after pre-training, like computationally more efficient. And this is true actually for one of the genomics foundation models. It takes quite a bit of less time to fine-tune. All of the others are more expensive. And so, I mean, this caduceus PH foundation model for genomics, I think it is doing some very meaningful compression. It's a very small foundation model that's trained on a lot of data, but it's very small. And so it is clearly learning something. Its performance, like its accuracy performance, is not as good as an architecture search approach, but it is very fast, and it's very. But even for accounting for all of this cost, it is faster to just do the supervised pipeline. And another question, right, is maybe foundation models require less data to do well, right? A lot of these tasks have a reasonable number of supervised training data points. Maybe we can reduce the number of tasks, and like the kind of idea behind few-shot models is, or a idea behind foundation models is that they can do some type of few-shot learning. I guess my first point here is that you do need to design better benchmarks. If your claim is that you're doing better on benchmarks, design the benchmarks that have the right number of data points that kind of you will do well in this regime and make us compete in your regime. We competed in the regime set. We did evaluate with subsampling. So if we do 5 times less data. And we can see, so here on the X, we just have a bunch of different foundation models compared to our approach. And otherwise, we compare, what happens if we train on all our data, so the orange, versus what happens if we train on a 20% subsample. And results are, mixed. In genomics, some models do a lot, all the models do worse. Some models do a lot worse. Some models do slightly worse. In satellite imaging, results are, I think, again, mixed. So again, all models do worse. And I would say it is true, at least for these cases, that at least some of the foundation models do better on, say, 20% less data. So there is something useful here. But again, these weren't the benchmarks that were created. And indeed, at some point when I was presenting this talk to other people, they were saying, oh, well, these supervised learning don't have enough data to fit the foundation models to fine-tune them. So it's been, because kind of the paradigm in supervised fine-tuning these days is to fine-tune on a dramatic amount of data. And again, also for time series, some of the foundation models do also dramatically worse, and the supervised approach does slightly worse. Maybe the decrease in performance is roughly similar to many of the foundation models. So to summarize this, I think we've seen that a lot of resources have been trained to train these specialized foundation models, but they are beaten on their own benchmarks, the benchmarks they set, at least, by cheaper supervised models. And I guess the summary is, to accurately measure this type of progress, we should have difficult tasks. One's not solved by supervised learning. So, for example, tasks where we subsample the amount of data and kind of do things in the few-shot regime. They should reflect use cases that are actually targeted by foundation models. So foundation models can do things like maybe zero-shot learning as models. And they should also cover a diverse range of applications, maybe that kind of a single supervised pipeline can't handle all by itself. And so kind of the bottom line here is before you want to use this foundation model, check if you can run a well-tuned supervised pipeline, whether that suffices for your problem. Yes.
Have you also thought about measuring the robustness of the model, say distribution shift, power distributions, comparing the FM fine-tuned version versus the fine-tuned version?
I see. Yeah, we have not tested that specific case. It's like just outside of the benchmarks that we considered. There's a lot of tasks that we have to do. I don't know if I would expect, you might intuitively expect a foundation model better because it has a bunch of data. But I guess we intuitively expect the foundation models to do better. But I don't know. Yeah.
This is a good point to ask, about are you going to move on?
Yes.
Yeah. So, do you do anything better than AR models for time series?
Is there anything better than AR?
Yeah. Yeah.
Right. So it depends. I guess so. We tried our architecture search approach for AR models. Because of the kind of non-IID nature of time series, we had difficulty fitting the architecture search approach to the time series models. People can of course do it, but our specific approach was a little lagging there. I think there has been a lot of development in time series foundation models. There have been people who have introduced new benchmarks. The benchmarks for time series are quite old and quite weird. It's just a bunch of electricity grids, electricity usage things, and so people are trying to develop benchmarks that may be more and on those benchmarks. But this of course was post our work. But on those benchmarks and with maybe constraints on the data, that time series forecasting, you can do, of course, you can't do AR so much. You can do it to some extent. It depends on what you mean by zero shot. But in those cases, there are better foundations. Yeah, I guess it is kind of a weird thing because the auto arena thing I mentioned, right? That was first evaluated not in a foundation model context. It was evaluated in a supervised model context, where it was being compared against a bunch of supervised models for time series. And so if those supervised models are being beaten by a linear, which are being matched by this AR model, then those supervised models are also. Yeah. So it's just kind of a cascading issue. Okay, so the second part of my talk, I'll go into what the architecture system is that underlie this investigation. And this is work that was led by Nick, or at least partially led by Nick. He was here somewhere. Hello. Yeah, so I'm a master's student at CMU, and I was a senior PhD student here. And also by Junhong Shen, who is a senior PhD student at CMU. And it also was joint work with other collaborators, Tree, Liam, Rambo, Chris, Fred. I don't know if he's here, but he's also a professor here, and Amit. Okay, so remember what we wanted to do was we wanted to do the simulated supervised workflow. We don't have enough time to do human model development for all of the supervised tests, so we're going to instead find good models using architecture search. And we need a method that efficiently returns high-performing supervised models and works on multiple data modalities and dimensionalities. Okay, so before going into that, what is neural architecture search and what is a neural architecture? So an architecture is a labeled graph that defines some model class that we're trying to learn over. And specifically, it specifies what operations, additions, concatenations, multiplies, convolutions can be applied to the input to output of prediction, and in what order are those operations applied. It does not specify the parameters of those operations, and those are set by the training data. And it uses the same training data that you might later train on to define the architecture by setting the graph's edges and operation labels. So it's kind of a fully supervised, it's just an addition to the fully supervised pipeline, just like hyperparameter tuning, where you take the training data you have and you try to find a good architecture on that training data. And why might we use it? So the kind of motivation here is that state-of-the-art architectures became extremely complex very quickly. So ImageNet was in 2012. By 2016, you had this complicated thing called the Inception v3, which took a bunch of Google engineers, however much amount of time, to develop where the output heads was and what convolutions to use and so on. And there are too many tests that we're interested to hand select a customized architecture for each one of them. And you might have a question of, isn't this just some type of hyperparameter optimization? And the answer is yes, but there are many more hyperparameters. So there are combinatorial, meaning hyperparameters here. So usually there are many more. And the hyperparameters are architectural. And this allows us to do things that with regular hyperparameters might be more difficult to do. And maybe a second question is, isn't architecture search very inefficient, right? I promised you that the compute budget of our entire pipeline was competitive with just fine-tuning this foundation model. And the answer is yes, if you fully train each model from scratch for the entire training budget, architecture search is indeed very inefficient. In practice, there are so many good heuristics for architecture search. There is train, do the search on much smaller models and then blow them up and do it on only a subset of data and so on. And there's the key approach called weight sharing, which is maybe like the key to what makes at least our approach works. And this was introduced in 2018. And the idea behind weight sharing is instead of training many, many discrete architectures each at a time and seeing how well they do, train one architecture that is a combination of them. So train a super network that encompasses all of the entire, not complete graph, but certainly the graph that is the union of the possible graphs. And then train that architecture and some weights that parameterize whether you turn on specific edges or not, and then discretize those weights after the training. That gives you an architecture. And then you can retrain that architecture on your data. And this supernet, you don't, of course, again, you do the previous heuristics I mentioned, you don't train on your entire data. You train on maybe a much smaller subset of your data. And the takeaway here is that with the right heuristics, architecture search does have less overhead than training a signal. So in our case, it's usually like 10 to 20%. The total training budget is architecture search. And then, what is architecture search actually useful for? So here I'll have a sequence of tweets. This is a professor at CNU. And right, so as you mentioned, there's been a ton of work on architecture search. And Zach does not know of any major mainstream neural network architecture that uses components that result from this line of work. And I think this is maybe a little unfair. I think people did at some point at least use things like swish, which is an activation function. I can't promise that that's super important, but people used it, I think, and that was automatically discovered. But it is true that I don't really know of any kind of very important, everybody knows them, architecture components. So So there's a response to this from Colin. Colin is, he's, I think, head of research at a company called Abacus AI, but he was a grad student at CMU. And so his response to this was, you can use architecture search to get state-of-the-art on ImageNet, and that's what's been done on ImageNet. And so the point of architecture search, according to him, is that you don't want brand new architectures. You want to make them existing ones better and more efficient. So that's nice. Our argument is that architecture search research has, as I kind of argued before, focused very exclusively on CFAR and images. So there have been 1,000 papers. They've focused a lot on CFAR and ImageNet with some kind of work on speech and natural language processing. There have been a few papers here and there on biology, time series, I think tabular data. But kind of the dominant mode of research and kind of the benchmarks that people actually believe in have generally been for image data. And this is despite the fact that when I tell you architecture search, the kind of promise that you might have in your head is, oh, any person, any scientist in any domain can use neural networks now because they can discover a good architecture for their task. But this is not what's being evaluated. What's being evaluated is how good does it do on vision. And so we asked this question, does architecture work on tasks outside of computer vision? And we built this benchmark, it's called NotBench 360, to find out. We collected 10 tasks. They were drawn from a variety of domains. There were some hand manipulations, there were some proteins, there was some genomics, there was some satellite imaging. But they were all fairly small tasks. And it seems that kind of standard NAS architecture search approaches only beat kind of the expert designs in those domains. And these were kind of domains where there wasn't a lot of machine learning work, right? These were diverse domains. This wasn't computer vision. But they only built the expert designs on those on 3 out of 10 tasks. And this is despite the fact that as I mentioned, use case for architecture search is maybe the most important one, right? Give me an architecture for any task I may have. And they're also the tasks we care about when we're evaluating specialized foundation models beyond vision and text. And so we started looking into this, why did the best architecture search models fail? And we kind of came upon this at least idea, that maybe that architecture search is really focusing on a really strong graph topology, like how are all these operations connected and how is the information routed? Yes.
So when you're saying you tested NAS, did you search was it cell-based NAS, like darts type of thing? Or there is okay. So you focused on cell-based search.
Yeah, cell-based weight sharing type search. And so we kind of had this thought that methods like darts and all these other approaches, they're really focused on how do I get a good graph topology? How do I connect a bunch of different nodes with a bunch of different information and information flows between those nodes? And put the right operations in the right place. And we looked at this, and then we looked at what humans have been doing for the past decade, and they've been developing these architectures, and the breakthrough ones all have actually the same topology. They all have kind of this residual network topology, where you have an input, it gets passed through some operation, some weighted parameter, and then it's passed also through the identity operation. They're recombined somehow, and then it goes forward, right? Many of you are hopefully familiar with the idea of kind of a residual network. So in the original ResNet, this was a convolution, but you see similar things in a transformer. So in a transformer, it has a residual layer interspersed with multi-bit attention. Certainly one of the most popular architectures in solving partial differential equations called the Fourier neural operator. You again have this feature where you have this residual network, but instead of a convolution, you now replace it by a frequency filter. You do the Fourier transform of your data, you apply an element-wise product to it, and then you do an inverse Fourier transform. And so our idea here is, what if we stop doing this graph topology stuff, and we just fix a topology and search for good operations over one expressive search space? And I won't go into too many of the details of the method that we went into, that we came up with. The method is called XD for expressive diagonalization. And it's basically built, it basically designs a search space containing many operations, including convolutions, including these FNOs that I mentioned, including graph convolutions. But it turns out like it does well on some tasks, gets good networks, but is really expensive. Really expensive to train. To the point where we couldn't really even evaluate it on space research. And so we did something much simpler, still staying with the same idea of ignoring the graph topology and just focusing on one core operation. What if we came up with a method that just finds the right kernel size and dilation rate to use at each layer of a convolutional neural network? And this is a method called Dash. How it basically works is during training, it will consider multiple different kernel size and dilation rates of your convolutional filters. So you have a bunch of different kernel sizes, you have a bunch of different dilation rates of separations between the filters or gaps. During training, you will upweight or downweight some weights assigned to these parameters. And this is kind of the core idea of weight sharing. After training, you will discretize those weights. So you will assign weights to these kernel size and dilations, and you will discretize, you take the maximum one. And you do this at each layer. So you find a good kernel size and dilation rate at each layer.
So yes. This is now you're going back to just tuning a bunch of scalar parameters.
So yes and no. It is, you're tuning a bunch of scalar parameters, but they are architectural parameters. You can do weight sharing with non-architectural parameters. That's kind of the key distinction between architecture search and weight sharing, where in architecture search and hyperparameter tuning, because weight sharing kind of depends on the parameters not being dependent only on validation signal. Like they have to be able to like be trainable with your model and like affect like the hypothesis class kind of directly in a parametric way. Whereas an architectural parameter, non-architectural parameter, it does not.
Yes, compared to learning data, saying you learning data, like the size of the number of neurons you have to train the model from scratch. Whereas here,
yeah,
are able to start in that data.
Yeah. So here, the key thing here is that we're able to, even though it is the case that we have many fewer hyperparameters, and there you can view them as kind of scalars. It's still the case that we can kind of combine these, like the different options together in like one forward pass, and put them into kind of our empirical risk. Okay, so this Dash algorithm, it fixes the topology and searches for good kernel size and dilation rates at each layers. As I mentioned, it finds good architectures faster than it takes to train the same architectures. It does this by heavily subsampling the training data during the search process and training smaller architectures like smaller channels or fewer channels. And now it beats 7 out of 10 expert architectures on this NASBench 360 benchmark that we came up. And it was adopted also by a second place team at this Automelt Decathlon competition, Nick Wren at NeurIPS. They, I promise, were independent of us. They did well and only got, I think, outperformed by some guy who was really good at Kaggle. Like he won Kaggle a lot. And these were completely new tests and not related to NASBench 360. Right, and so this is the approach that we adapted to show that supervised learning is competitive with specialized attempts. So for the satellite task and the genomics task, what we did was we took this architecture search approach and we just ran its pipeline on those tasks to do better than foundation models. So that's exactly what we did, except we also did modify it slightly. We added we added a training loop to turn the non-architectural hyperparameters. Using a standard architecture search in an inner loop. And for some of the foundation models, we also did some architecture search, some hyperparameter tuning for those, because there were many tasks. We did tune hyperparameters for the fine-tuning of foundation models to kind of make sure that we were giving what they should be. Yes?
Dash algorithm seems to focus on speed up the perspective, but considering the performance, do you consider design some specialized in-search spaces for neural architectures because they are cheaper and the search space is fixed even random search can
Right.
the good model is incomplete. Another perspective.
Yeah.
Research space.
So it depends on what you like. There's random search and there's random search space weight sharing. Random, both of them could work on the search space. The issue with both of them is that random search kind of forces you to train the full model. I mean, you can do the kind of subsampling approach too, but usually what people do in random search is they'll try a bunch of different options. And so they can't do this type of weight sharing approach where they train multiple architectures at the same time. So that type of speed up is not possible. You can do random search with weight sharing where you subsample kind of random architectures without doing kind of a tuning process, and then just pick out the architectures based on the weights that you find. And that works okay. I don't know if it's state of the art. Yeah, but it is a fair point that you can kind of expand your search space to include other things, and maybe get kind of more specialized art. Okay, so we have the summary of the second part of my talk is that you have kind of this broadly effective architecture search approach. And if your CNN is basically not doing as well as you like, if you're trying to make it beat a foundation model, you should try Dash. It works on different input dimensions. It's often less expensive than training a CNN from scratch on all of your data. And we've evaluated at this point on the 10 tests in Aspects 360. We evaluated on, or someone evaluated on the AutoML decathlon tests. And of course, we evaluated it for this investigation. So in some ongoing work, we've continued looking at how we can do well across modalities foundation model. One approach that's extremely popular, I think there was even some discussion of it yesterday in the machine learning lunch meeting, was recent work showing, was kind of building upon this recent work showing that you can fine-tune text and vision FMs on completely different modalities and get results that are competitive with specialized foundation models. So the idea here is you start with BERT or whatever you trained on your massive text corpus, and then fine-tune this foundation model on genomics tasks, on time series tasks, on PD solving tasks. And it turns out that this does remarkably well, even sometimes compared to the foundation models in domains. But there are challenges of scaling this to kind of the many billion parameter models. I don't think we've seen that this approach works when it's kind of a BERT model with a much larger model, say a llama model. And then, of course, there's the question of our work that I presented shows that you can do quite well with just supervised learning. Will this approach work when we introduce better benchmarks that don't get beaten or that don't do well or that aren't solved by supervised learning as well? And of course, how do we develop better specialized foundation models that do better than the ones we've discussed here? Well, we haven't maybe seen the BERT moment. We do have kind of some directions of doing better domain-specific modeling, and I think maybe the kind of core solution would be to develop better use case-aware benchmarks. And maybe the kind of gold standard for success here is the CASP challenge for protein folding, which one is kind of like the driving force behind machine learning methods like AlphaFold. And here again, there's been kind of developments also for this case and also for pre-training data. For example, in PD solving, a very large data set of simulations was recently released to train your foundation models on. And by developing kind of this high quality and domain data, hopefully we can get to a point where we actually see better performance from these specialized foundation models relative to supervised learning. So thank you. These are all my collaborators, and I'm happy to take further questions, or please email me or see my website. Thanks.
Yeah. Thanks for the great talk. In the first part, you also tried applying non-trainable approach for finding the right way of fine-tuning the model. Like fictional
yeah.
Also,
I think that's a great question. I think maybe it really suited.
Yeah, yeah.
It's a good point. Like you can in principle maybe do it. I think there's two issues from a model. Architecture search has been done for transformers, but and probably going to be. But one could in principle do it. But it certainly isn't kind of a part of any standard pipeline.
But there's, I guess, like it's pretty like feel like that.
Yeah, yeah.
Wait, and then it's
Right.
there are a few key
Yeah.
That would be a better.
Yeah, I agree. Yeah. Yeah, I think like my philosophy on like hyperparameter tuning for these foundation models is that we are academics. We can't do hyperparameter for all of these tests and all of the tuning. And we kind of are forced to trust that the folks did as much fine tuning hyperparameter tuning. And like this is just a computational verdict. We really can't find it.
You more than
Sorry.
that's what one thing that
Yeah.
actually we not like see my for on that.
Right, but we didn't like the numbers we reported here. We didn't do any fine tuning. Like, okay, we fine tuned in the satellite test. We did some, but like for genomics, we took numbers because we had to. We couldn't afford to fine tune all of them. And in the time series models, those are very big. We couldn't afford to fine tune all of them. So we like Dash is efficient. It is kind of very specialized to any CNNs. Weight sharing isn't, of course. You can do weight sharing for